We're going to start off acid-base reactions and understanding them by starting off with some drugs, pharmaceuticals. So you can't understand pharmaceuticals unless you understand organic chemistry. Now, acid-base reactions are discussed extensively in general chemistry. So if I said, hey, general chemistry student, 101 student, tell me, is LSD an acid? And they might say, well, colloquially, it is called acid. But I'd have to get some measurements, some data. I'd have to look up its pKa, or maybe I'd have to calculate its equilibrium constant in the lab. And that would help me determine if in the presence of a suitable base, I could get it to react with it. That would determine it's an acid. So they would need the evidence. They would need the data, right? Organic chemists use that data, of course, but we don't crunch the numbers the whole time to figure it out. We'd actually be able to look at that structure and say, a funny thing that it's called an acid actually, because it's not. It doesn't really act like an acid. At the end, how did I do that? Interpreting the structure. So structural features will let you know if something's an acid or base, at least a strong one. If you're not sure, then we consult the tables and the numbers, but we could at least get a trend established and know where it should fall. And then for nitpicking little comparisons that fall close together, then we go back to the table and take our time with those numbers. So we're going to start off by reviewing a little bit of what is expected foundation to continue the discussion to where you would be able to look at this by the end of this unit, I hope, and also say, yeah, that's not an acid. Okay, so terminology to get straight. And it's some of these simple things that really explain it best, but sometimes it's hard to pin down, even though you knew it somewhere in the back of your mind. Bronsted-Lowry acid and base. So that definition we need to revisit. So in other words, what makes something an acid when you're talking about an acid-base reaction? It's a proton transfer reaction, right? So what's the acid's job? The acid lets go of the proton. So we're going to phrase that here. A Bronsted-Lowry acid donates a proton. I'm going to be abbreviating proton as H+. A Bronsted-Lowry base, therefore, is the one that takes the proton, because it's a transfer, right? Accepts the proton. Okay, so when we say proton, we mean H+. We don't mean H. So what are the forms that, or the phrases we could use? We want to use the correct terminology. If we were to say hydrogen, we might mean, oh, we're talking about that atom that's attached to something, or H2 gas, that's also called hydrogen. So if we're just talking about hydrogen, we're not talking about a proton until it's actually removed. So a proton, if you look at a periodic table, a proton, a hydrogen missing its electron is called a proton because it literally is just that. Its electron has been stripped. It has one electron. It's 1s1. I got a periodic table puzzle. It's way over here. One electron. 1s1 is its electron configuration. If you take that electron away, which is what happens in an acid-base reaction, and we're going to show how that actually happens, it has no electron left. It's now H+. It's broken the bond, right? And the electrons didn't go with it. There are times the electrons do go with it. So when you break a bond to hydrogen and the electrons choose to go with hydrogen instead of not going with it, that's no longer a proton. That's an H-. That's a hydride. The ide suffix, remember, is reserved for anions like chloride versus chlorine. So chlorine Cl2, chloride Cl-, right? So the ide suffix indicates that you have an H-, right? Okay, so you want to get those straight so we know what form we're really talking about. Okay, some more terms. Conjugate acid. Okay, I'm going to be abbreviating that Ca. It's formed from adding the proton to the Bronsted-Lowry base. Then the conjugate base is formed. I'm going to call that Cb. The conjugate base is formed from the acid that lost the proton. Let's look at another example. So another biorelevant one, lactic acid. You know, lactic acid fermentation, this is actual structure. Does that act as an acid? And the answer is yes. Can you think of what functional group is the one that loses the H? So if you're thinking about H's getting lost as protons, they're going to become a H plus. So surveying this, we know we have lots of H's on here that aren't even drawn. But which one has the bigger delta plus on it? Right, so it'd be either this one or that one. So those are the only two choices, because notice that this is not a polar bond. So if the H is going to become an H plus, that's easier for it to happen on a polar bond, and we'll see that soon. And then this is a carboxylic acid functional group. Those function as acids. So if you see a carboxylic acid, that's very likely the proton that's going to come off. So you'll have to be able to interpret that in large molecules. When there's lots of functional groups, you have to see which proton came off, right? So let's just add a base, plus base. Often bases are negatively charged, but they don't have to be. The lone pair is present sometimes instead. And remember, we have an equilibrium. And we can make one arrow bigger than the other, and if we know the direction of equilibrium. And so what happens is we're going to lose this proton, and it's going to go to the base. So that's the acid. We have our base, so I'm going to label acid. And obviously we wrote base, but I'll write it again, because we're going to write them in every, underneath each structure in every equation, but I'm making it generic this time. I'll make bases blue, because on the litmus paper they're blue, right? Conjugate base, let's do CB. So you're going to redraw lactic acid, but leave off the H. And the H did not take the electrons from this bond that was right here. So they're now on the oxygen. Okay, plus your base took the H and it's now neutral. Okay, so this is your, it has the H, it gained the H. So now it's the conjugate acid. I promised to abbreviate these, so I'm doing that now. Okay. All right, so questions that we need to answer. We kind of briefly went over what H is removed and why, but don't worry, there's a lot of more reasoning behind it that we're going to flesh out. That's kind of just a little peek into what the rest of the lecture holds. We're also going to answer how. How did we know we had this negative charge here? One hint with charges is your net charge on both sides have to be the same. So everything is summed together. This is neutral, negative. We have a -1 on the whole side here. That's the match here. You did something wrong with your what we call the reaction mechanism. So the mechanism will tell us how. And structural features will tell us why. And we just hinted at those about the polarity of the bond, but we're going to dive deeper into that. Before we go too much deeper, we're going to look at a little bit of review that we need to help get us through. So the next page, I'm kind of treating this as assumed knowledge. If this part is rusty to you, your textbook's not going to go much deeper, your organic book. It'd be time to go to the general chemistry book, but we're taking the consequences of this and building upon it, okay? So this is kind of what we're taking from your general chemistry multi-week study of acids and bases, okay? So label the Bronsted-Lowry acid base, conjugate acid and base in the reaction below. So this is water. Water does this thing called autoionization, right? Autoionization means in the presence of itself, it automatically ionizes. Okay, so that means water can react with itself, and one of them is going to transfer a proton. Whoever lost the proton, let's just assume they're in order, right? We're matching them in order, right? So what happened right here? I'm going to say what happened here. That gained the proton. That's hydronium ion, right? Hydronium, H3O plus. This is hydroxide. That lost a proton. And this gained a proton. Sorry, that was a little messy. Let me write that a little more neat. H plus, there we go. So the one that gained the proton accepted it. Therefore, this was our base. The one that lost the proton gave it. Therefore, this was our acid. So then that makes this our conjugate acid, conjugate base. Okay, now we are going to show how this proton is transferred. When we are explaining how something is happening, this is the reaction mechanism. Be ready to practice these a lot. Mechanisms will accompany every reaction we learn in the future, which is why we're starting off our reaction section with acids and bases, because it's more familiar before we start doing new reactions you've never seen before. So we've all seen proton transfer reactions before, but it's very unlikely that you ever showed how the electrons actually got transferred. So we're going to do that now. And I actually think that's the most exciting part of this chapter, is that in general chemistry, you've got to always say, determine, prove with evidence, acid-base. That's alone a cool thing, but then to be able to say, why? Why is HCl an acid? Why does it do that? Why does it have those numbers that tell us it's an acid? What about HCl makes it do that? What about sodium hydroxide makes it not an acid? The answer lies in its structure. Structural features will determine whether or not it wants to gain a proton or lose a proton. Okay, so let's illustrate what happened here by showing the flow of electrons. So the mechanism tells the story, tells you where the electrons went. There's a very precise way to draw them, okay? When you're getting ready to draw a mechanism, you need to show all the structural features. You can't write a condensed formula. You have to have the bonds drawn out because you might be breaking a bond, right? You actually will be breaking a bond because you're reacting. Lone pairs need to be shown because you will be using them, right, to make a bond in many cases. So notice how this has been turned into completely drawn out Lewis structures. Okay, so let's draw out the mechanism. I like to use red arrows for my mechanisms because, so if you have red handy, you can match me. Now, I'm going to try to illustrate that this became this, and it might help me to even label this again. So let's label this base, and this is our conjugate base. And let's label this acid, and this is our conjugate acid. Okay. Time for the flow of electrons. The base gained an H. How did it gain an H? Look what happened here. One of the lone pairs is gone. What did it do? Still has 8 electrons around this structure. So this is hydronium, right? All drawn out. Still follows the octet rule, but one of the lone pairs is gone. The lone pair, one of these two, got converted to a bonding pair. That must be who grabbed the H. It's like solving a little mystery. Who done it? All right, so that, you could pick either lone pair, it doesn't matter. So you pick a lone pair to take the H. But hey, you didn't make this giant complex with 2 waters stuck together. This went off by itself. And let's look at the changes that happened here. And let's have some arrows to show that. Okay, so look how precise I tried to be with this arrow. In fact, I'm going to make sure it's really coming to here. It has a tail and a head. So the electrons moved, they're flowing. So nothing landed here. This basically attacked the H, is how you could think about it. So the arrowhead had to go there, and this is drawn using curved arrow notation. So these are curly arrows. So kind of like we've done in resonance, right? Same sort of arrows, only now we're doing them between molecules to make them break bonds, as opposed to within the same molecule. Okay, so just before I draw the next one, I'm going to remind you we're looking at the flow of electrons during a reaction. So I have to abbreviate reaction, RXN. Okay, so the first arrow I drew was right here. Actually, I'll do that in, yeah, that's fine. So number 1, we will describe that when we're done. I need another arrow though, because clearly this shows that a bond formed here, and these are, now I have a giant complex, and I don't here. I need this arrow to match the story of what happened. So what happened was this hydroxide formed, which means this water lost its H. Well, we see it getting grabbed, but it's still attached here. How do we detach it? A clue lies in looking at lone pairs. Notice we gained a negative formal charge because we have that bonding pattern of 1 bond, 3 lone pairs. So we have, 3 lone pairs. We only had 2 here. There's that mystery solved, right? So we're going to show the bonding pair become a lone pair. Just like we had a lone pair become a bonding pair, now we're going to take this bonding pair. The arrow starts right in the middle of that bond because you're actually breaking it, and the electrons stay behind. And that's what makes it a proton, not a hydride. The electrons did not go with it. So this water took the H and only the H. This H ditched its electrons, landed on the oxygen. If you could describe that out loud, and it matches the consequent structures, you did the mechanism correctly. So I drew only 2 arrows. We're starting off simple. We're gonna have mechanisms that fill a page by the end of the semester. So, take this chance to really get this down so that it doesn't catch up with you later. So step 1, you should be able to verbalize a story with your mechanism. That arrow shows what? Bond formation. So the lone pair became a bonding pair. And then step 2, that arrow showed bond breaking. Now, this is not a step to memorize. Every mechanism is different. You can't memorize them. You have to work them out. So the sooner you get the logic of it, which comes only with lots of practice problems at the end of the lecture, then that should help. Okay, bond breaking. In other words, the bonding pair became a lone pair. BP to LP. All right. Now, some will say, once you do enough mechanisms, I'm talking hundreds, maybe thousands. I've had some Chem 212 students, or the Organic 2, where the light comes on and they go, okay, I'm okay, this is more of the same. It takes a while to get to that point. And I know we're all going to want that, but it's uphill learning curve for now. But when you say, okay, this is more of the same, they're absolutely right, because almost every reaction out of the hundreds we're going to do can be described in a more general term of acid-base chemistry. Does that mean all reactions are proton transfers? No. But it has a similar logic. A bond is made and a bond breaks. And we're just trying to find out which one and how that happened and how the electrons were flowing. So there's a more generic term for that behavior of something donating something or something getting attacked and something doing the attacking. Okay, that's Lewis acids and bases. So why did that not really come up as a big distinction in previous classes? Because most of the reactions you did were proton transfer. That's a subset of Lewis acids bases. So let's broaden this definition. A Lewis base donates a pair of electrons. Well, that did happen, right? So we're not talking about donating protons. That's Bronsted-Lowry acid-base theory, where it restricts its discussion to how the proton moved. We're talking about electrons now. So now that we've drawn a mechanism, we can talk about what electrons did. And notice this donated its electrons. It used to hog them as a lone pair. Now it's sharing them in this bonding pair. So this is our Lewis base. What are features of a Lewis base? It's got to have some region where it's electron rich. Oh, sure, oxygen's electron rich. Okay, so how did we know that? We've been studying polarity and that sort of thing, so dipoles, but consequences of drawing out the dipoles, as you could see, for example, a delta minus, delta plus for polar bonds, right? Delta plus. So let's put that feature on our list. How do we tell? Delta, the one that did the attacking, had the delta minus. So I'm actually going to do it in black so we can see delta minus. It may have a full minus, right? Because that would be even stronger, more reactive. We're going to use this term as well. Nucleophile. Loves the nucleus. Negative loves the nucleus, okay? But let me add one more to this list. Oh yeah, pi bonds are electron rich. just so we're used to looking at it. And lone pairs. So another word for Lewis base that in particular we're going to transition to, organic chemists love to use, is nucleophile. So we're going to be calling things a nucleophile if it does the attacking. It gives its electrons to grab something. I abbreviate nucleophile this way, but some other books also just do this, or they might even put the negative. Okay. Lewis acid. We're not talking about proton transfer. A Bronsted-Lowry acid gave the proton. So what would a Lewis acid do? If the Lewis base donated electrons, then the Lewis acid accepted the electrons. Therefore, if it's going to accept electrons, it better be willing to accept them by being electron poor. Something electron deficient is more willing to accept electrons. How do we tell that? Well, who is our Lewis acid? This molecule was our acid, but the arrows landed on the H because that H was a delta plus, right? If we draw out the dipole, now it becomes more clear. It makes sense that something that was a delta minus attacked a delta plus. So whatever the delta minus is the Lewis base. Whatever the delta plus was that got attacked is the Lewis acid. Okay, so that, notice these are both water, but water, remember it's amphoteric, it could actually kind of do both, but we'll look at some more obvious ends of the spectrum like hydroxide or sulfuric acid, and then move on to organic structures as well. Okay, so how do we tell something's electron poor? Well, in our previous example, we looked for a delta plus, but it could even be more reactive if it's a full-on positive charge. We also might see carbon with its open octet. All right, so it's a C+. That's a great Lewis acid. So any open octet's electron deficient. Okay. That means it loves electrons, therefore its name is going to also be, it's synonymous with Lewis acid, is going to be electrophile, and we'll abbreviate that E+. We're going to be looking, every time we learn a new reaction, we're going to say, who's the nucleophile? Who's the electrophile? Okay, so we're going to get familiar with that just by using it. So let's reframe our terminology. And instead of looking for the Bronsted-Lowry acid base for who's transferring protons, let's look for the Lewis acid base. And the Bronsted-Lowry acid will be the Lewis acid. So it's really not that difficult, but you don't always have to think in terms of proton transfer, and that's why that definition's there. This chapter, that's all you worry about, though. So that's just laying the groundwork, so when we expand our logic later. So the electrons are getting donated. Donated electrons means it's a Lewis base. AKA nucleophile. Accepting electrons means it's a Lewis acid, AKA electrophile. Okay. That gave us hydronium, which you need to be familiar with that H3O plus, hydronium, plus hydroxide. Okay, so we got this down, right? So once you learn a mechanism, this is the basic idea behind acid-base mechanism. You got to find out who's attacking to get that proton and how, and show whatever proton you grabbed, that bond breaking. So we don't have to use water. We could use other acids and bases. And we can make small tweaks in the structure where it's not the business end. In other words, where no arrows, no curved arrows are touching, and expect the same result. For example, if water has that reaction, we can expect alcohol to have that reaction, because notice that one end of it was untouched. So we'd say the business end kind of happened here, and this was not part of the party. So look, go back to here. So you notice how we didn't do anything with that other H? So if we replaced it, made it variable, replaced it with other groups, we should still expect the same mechanism, because the business end stayed the same. The functional group aspect stayed the same, you know, the function of the mechanism. So notice that we swapped that out. So in our group, on an OH makes it an alcohol. Okay, so now we're going to do a quick recap of some things that we use to quantify strengths of acids, just because might refer to these numbers or look them up, especially if it relates to something lab related. So we don't want to be totally in the dark if that was a long time ago for you. So just a few things to remember. We often write out very generically our acid plus our base. So HA, that would be our acid, and then in the presence of water, then the water would therefore have to act as a base in this case, because this would be presumably a stronger acid than water is, right? So that means the equilibrium would favor the direction of reacting that strong acid, ionizing it to form the conjugate base, and then hydronium, conjugate acid of water. So let's label this. Acid, base, conjugate base, conjugate acid. So these are partners. The base has a conjugate acid, the acid has a conjugate base. And we found out that arrow was bigger using the data, so obtained experimentally. So in other words, we would say, okay, the concentration of the products over the reactants, right? So we say products, that's how you get equilibrium, over reactants. That's the generic form, but if we have more than one, then we put all of them in. So A minus, concentration of A minus, times the concentration of hydronium. So conjugate base times hydronium. Those are products. Over reactants, HA and water. But remember, water is assumed to be present in large excess compared to the acid, so we could neglect its contribution to the equilibrium constant to simplify the math usually. So we'd usually do that, right? So that's really the K equilibrium, but when you acknowledge that water doesn't change very much, concentration of water, then we now call that expression the Ka. So let's write it out again. Products over the non-water reactant. Okay, so if you were to do this, if you take acetic acid, okay, so acetic acid is vinegar. It's got the acetate, the methyl carbonyl with an OH. So it's a carboxylic acid with a methyl. So the Ka for acetic acid is 1.74 times 10 to the negative 5. So almost all organic acids will have 10 to the minus something. And sometimes those numbers are harder to remember once you throw exponents in there. And we use these values actually quite frequently. You have a table, you should have a table easily, nicely organized in your book, and we'll fill out our own. But we don't like, if you notice, chemists manipulate numbers until you get kind of like a nice, more aesthetically pleasing number, not a mouthful in other words. So we'll change the scale. Like for example, angstroms, you don't see used anywhere as a unit, right? For bonds, it's 10 to the minus 10. And that's only because we want to say a bond is 1.2 angstroms or 0.54 angstroms or something like that. The length, we don't want to say times 10 to the minus something. So that's the whole reasoning that we do this log, so that we don't have to deal with the exponents and we can just remember a nice number like 5. And so watch this. pKa, little p, remember, equals, so p is an expression that means negative log, like pH, right? It's negative log of the hydrogen ion concentration. So same for pKa. So it means negative log of Ka equals negative log Ka. So that happens to equal 4.76, which we often just round off to 5 because we're not usually splitting hairs with those values. And that's an easier number to remember once again. So you're working with acetic acid. You think about vinegar, you say, hey, I know vinegar is acid, has a pKa of 5. That's something you might remember, right? So do you want to watch me write a bunch of structures and then you just copy them? You might, and if that's the case, we all have days like that. You can fast forward because that's what you can do. But I highly recommend you take this chance to stop and draw the conjugate base, right? So here's our acid, and I made it easy on you by making the proton that comes off red, take off that H, draw the consequential product. So you're just drawing what the conjugate base of this. Fill this out. Okay, then come back and check your answers, okay?
Because you know I'm all about that bass, no trouble. I'm all about that bass, no trouble. I'm all about that bass, no trouble. I'm all about that bass, bass.